Hello and welcome. This is the solution to quiz 4. The term that is used to indicate the degree of agreement with the true value is, that's pretty much a definition of the word accuracy as we use it in this class. Precision would be the repeatability. Qualitative might relate to measuring a particular trend in the right order, but not having the particular quantitative agreement with maybe some published values. Qualitative and quantitative, if you said quantitative here as the answer, that's, I don't know. I might wonder if quantitative is close enough to the right answer to be worthy of credit as well. So if you were debating between accuracy and quantitative, quantitative kind of does generally refer to some agreement with some sort of true value. I'd say maybe it's more relating to a published attempt that's not necessarily the exact true value per se. Like true value is meant to be, the mass of an object has a very specific mass, and can you repeatably and accurately measure that particular mass with another tool. If you do a set of experiments and come up with, and establish some value for a particular quantity, that's not really the true value, that's just some experimental quantity. So quantitative is usually more of an agreement with some experimental quantity than necessarily the quote unquote true value. So this is just more of a definition of that particular word. Number 2, which of the following statements is correct? A heterogeneous mixture must contain at least 3 elements. Let's come back to that one in a second. A mixture containing 2 compounds must be heterogeneous. That does not sound correct, because a mixture could contain 2 compounds but be homogeneous or heterogeneous. So B would not be a true statement. A homogeneous mixture must be uniform. That sounds correct, because a uniform mixture is kind of the definition of what homogeneous means. So something that is homogeneous is something that is uniform throughout. So C is sounding like the correct answer. Let's go through the others. A pure substance must contain only one type of atom. You can have pure water that contains 2 atoms, H and O. So that would not be a true statement. So D is incorrect. And then A, compound may contain only one type of atom. That is incorrect, because a compound must contain at least 2 types of atoms. It has to contain at least 2 different elements. If we go back to A heterogeneous mixture must contain at least 3 elements. The reason why I wanted to come back to this one was just the thought that a heterogeneous mixture, generally you would think it should contain 2 different substances, and the substances should generally be different atoms, but you could actually have a heterogeneous mixture of the same substance. Just if you had, the liquid in equilibrium with the solid, like imagine a glass of ice water, that would contain one substance, but in a heterogeneous mixture of the solid and liquid forms of that substance. So this is definitely not a true statement here. You could have a heterogeneous mixture with just actually one element. If you thought of just some noble gas like argon or something being in equilibrium, say between its gas and solid state, where you have the gas and solid together, that would be some form of a heterogeneous mixture of just a single element. So so C is the right answer on to this one, number 2. Okay, so number 3, consider the data obtained for the length of an object as measured by 3 students. So our students are A, B, and C here, and we have them doing different trials, it looks like. So the length is known to be 14.54 centimeters, which the conclusion summarizes the data. Okay, so we know the length is 14.5 centimeters. Probably what let's see if we can get around calculating anything here. B seems to be pretty far off. A might be pretty close on average, though they've got a pretty big spread. C, 2 lows, 2 highs, and 1 high. So C might be a little bit further off than A without doing any calculations. Okay. And so then which work was most precise? I think B is definitely the most precise work, because the measurements are closest together. And A is looking more accurate. I might have to actually crunch the numbers to be sure, but let's go through some of the choices here. So B has done the most precise work. B has done the most precise work. C has done the most precise work. I don't think that's true. I don't think C has done the most precise work. A, big spread there. So we might be calculating like an average deviation if you use a calculation that maybe you use in the lab. But I don't think we even need to do that calculation. I think we can just tell by quick inspection that B's spread of the measurements are definitely much closer together than A or C. And so now we're choosing between whether A or C is more accurate. Let's just, I guess, crunch, even though it seems pretty clear that it's A. But if we wanted to be sure, we just do a quick average on A, because whichever one comes out on average to be closer to the target is going to be the right answer. So I'm just adding up all A's, dividing by 5. That gives me 14.5 for the average. And 14.4 times 2 plus 14.8 times 2 plus 14.9. It's pretty clear that it's A. If I divide this by 5, that's 14.66. So we're, much closer, or not much closer, but a fair bit closer with student A. So right answer here would be B has done the most precise work, and that A is the most accurate. Moving on to 4, the result of which calculation below would correctly be reported with a total of 3 significant figures. So we got 15.56 minus 5.25. So that's going to be 4 significant figures. So all 4 of these are significant because we're going to round to the tens placeholder, so that's not 3. If we multiply them together, multiplication's easy. I don't even need to do the calculation. 4 sig figs times 3. I know that's going to be rounded to 3 sig figs. And so then C, if I take 3 sig figs plus 4 sig figs, that's going to still be 4 sig figs because of if we switch this to adding instead of subtracting, then we're still going to have all 4 digits being significant. So only B is would correctly be reported with a total of 3 significant figures. This up a little bit. So number 5, to how many significant figures would the result of the below calculation be reported? So we got 3 times 4 divided by 10. One of the things that's kind of interesting, if you do that in a calculator, it says 1. Wait, that doesn't make sense. I did 3 times 4 divided by 12. 3 times 4 divided by 10 is 1.2 is what my calculator says. Okay, so if you look at your calculator, you say, well, it's 2 sig figs, and you go with 2, that's probably not the right answer. So what we need to do is do a little bit of thought here. We multiply 3 times 4. The result of that calculation should have 3 significant figures. So that's 12.0 kilograms times meters. We're then dividing by 10.0 seconds, so 3 sig figs divided by 3 sig figs. We should report this with 1 extra 0. So remember, our Sig Fig rules, we're doing like one of 2 things. We're seeing if we need to round our results to some shorter number of placeholders than our calculator might say, or 2, we're actually seeing if the result is actually a bit more accurate than what our calculator might say, and we're like tacking a 0 on. So we're saying with the quality of these digits, we can say that this result should be 1.20, and we're thinking like our plus minus here is waffling in that sort of hundredths placeholder, not in the tenths placeholder. So we give all 3 sig figs here, and then this would be like kilograms, meters per second squared if we care about units. So 3 sig figs for this problem. Number 6, we're given the mass of some piece of hafnium is 3.322 grams. We're given some length units. We're asked for the density, but in grams per cubic centimeter. So we could do this a couple ways. We could just calculate the volume here, just using length times width times height, and then keep it in cubic millimeters. So I'm going to do that right now. So I'm just going to go 25.0 times 40.0 times 0.250. So that works out to be 250 cubic millimeters. That 0 is significant. All 3 times 3 times 3. So all 3 are significant. Not really a sig fig problem. Doesn't look like anyways. But what we might then do when we need to calculate our density, I might do it like this. I might take my 3.322 grams, and I'm going to divide by 250 cubic millimeters, and then I can use my conversion that there's 10 millimeters in a centimeter. Now, if you forget or you struggle with these prefixes, you might just say there's 1,000 millimeters in a meter, then do 100 centimeters in a meter, work it out that way. So you could do this conversion a couple of different ways, but a centimeter, there's 10 millimeters in 1 centimeter. So we can use that conversion if we can use that one as well. But we've got to cube that conversion factor. And so when we cube the conversion factor, if we do this in a calculator, it should be 3.322 divided by, and I might do parentheses, 250, And within that parentheses, divide by 10 caret 3 for 10 to the power of 3. Close parentheses, hit enter. I get 13.288. And so that would be 13.3 rounded. So this works out to be 13.3 grams per cubic centimeter. Now, one other approach we could have done is just convert these to centimeters right off the bat. So you could have just said, well, what if we just do, instead of calculating the volume in cubic millimeters, what if I just converted 25.0 millimeters to centimeters? So that would be 2.50 centimeters. This would be 4.00 centimeters and 0.0250 centimeters. So we do that calculation, 2.50 times 4.00 times 0.0250 works out to be 0.250 cubic centimeters. And if you remember, we'd said you take the 250 if we want to check this, divide by 10 to the power of 3, and that's the same, it's 0.250 cubic centimeters, so it checks out. So we could solve this problem a variety of ways. You could convert to centimeters right off the bat, and then plug directly in cubic centimeters. You could keep it in millimeters, and then convert. There's not one right or wrong way to solve this problem, but there's a key that no matter how you solve it, you should come up with 13.3 grams per cubic centimeter. Okay, so moving on to number 7, how many milligrams of mercury, which has a given density here, are contained in 375 nanoliters of mercury? So we have the milligrams of mercury is what we're looking for, so we can start with that. Good trick in dimensional analysis is to start with what you're looking for, so you're not confused ever of what it is you're trying to ultimately get to with your dimensional analysis. We can then start with what we're provided and see if we can solve the problem that way. 375 nanoliters. So nano is referring to like a small unit, so there's going to be a lot of those nanoliters in 1 liter. If you had the other type of prefix like the mega and the giga, that's kind of the opposite. So if we had like 1 gigaliter, then that would be like 10 to the 9 liters in 1 gigaliter. So like if you're comparing the difference between like the gigaliter, there'd be, one of these would be equal to 10 to the plus 9 liters. So it'd be a whole lot of liters in 1 gigaliter. And the nanoliter is kind of the opposite. 1 nanoliter would actually be equal to 10 to the minus 9 liters. So 2 conversions, you always have 2 ways you can convert. You can imagine dividing both sides by 10 to the minus 9. And if you do that, then you get 10 to the 9 nanoliters are in 1 liter. So there's 2 ways to give any conversion factor. You can say how many, for 1 liter, how many nanoliters are there? Or you could say for 1 nanoliter, how many liters are contained in that unit. But anyways, where this kind of helps us is we can convert to milliliters now. I would probably do this in 2 steps, at least in my head. I couldn't do this without maybe breaking this apart to go to 1,000 milliliters now in a liter to get over to the milliliter unit, so I can use the density now. So I can use 13.534 grams per milliliter. So milliliter cancels, liter cancels, nanoliter cancels, and we have grams. Now we do need to do one final step, which is to convert. I'm just going to go ahead and erase this stuff here. And we need to do one more step where we convert 1 gram to 1,000 milligrams. And we stop and calculate 375 divided by 10 to the 9, 10 caret 9, multiply by 1,000, multiply by 13.534, and then multiply again by 1,000. We come up with 5.075 ... So that rounds to 5.08. 3 sig figs, perfect. More sig figs than 3, perfect sig fig, so 5.08 milligrams. Okay, what I wanted to mention with this here is when you're putting this into your calculator, sometimes I see students do, say, 375 nanoliters, and then divide by 10E10. Yeah, so if you do 10E10, that would mean 10 times 10 to the 10. That's not what we want to do. That's actually 10, or I'm sorry, not. If we do 10 E, probably want to do 10 E to 10, that doesn't make any sense. If you do 10 E9 in your calculator, the problem with that is that's 10 raised to the power of 9, which is equal to 10 to the power of 10. So if you entered in here 10 E10, then you probably were off down here by a factor of 10. I think you'd have 0.508 milligrams. And the thing you'd want to do is either just literally do 10, caret 9 for 10, to the power of 9, or you could do 1 E9, because that would be 1 times 10 to the 9. And that's usually what I do, because usually I am more memorable of where the E button is on the calculator than the caret button. But if you're going to use the E button, just do 1 times 10 to the 9, and then that's 10 to the 9. Okay, so hopefully that's just a simple reminder on calculation. So if you got 0.508 instead of 5.08, you probably did 10E10, and then hopefully now know not to do that. So number 8, what is the result of the below calculation expressed with the correct number of sig figs? So one more sig fig problem here. So we have 3 sig figs plus 3 sig figs, but we got to sort of either write the numbers out. So we might want to go to the whole number. So that would be this. That would be the second number, good to this placeholder. We do our arithmetic. We get 2, 0, 6, 11, 62. So all 4 of those digits are going to be significant now. You could keep the exponent and add these together as well. So you could have just done this and then add it up this way. So you could have done the problem or thought through the sig figs in a few different ways here, but the key is you end up with 4 sig figs once you do the addition. And then when we divide by 4 sig figs, we're going to keep all 4 significant figures. Okay, so we don't even need to know the actual answer because, we're just really choosing the correct number of sig figs here. That would be A. All 4 of those digits are significant. The key is when you add those 2 numbers together, you get an extra significant figure because we got to keep that digit to the tens placeholder if we write the whole number out. Or we got to keep it to the hundreds placeholder if we keep the exponent as 10 to the 3. So the key is that this is just like if we did 449 plus 713, that would still have 4 significant figures in the end. Likewise, the addition, even with the exponent. So don't let the exponent here, the times 10 to the 3, confuse you in this problem, or somehow arrive at a wrong answer. We just apply the same general type thoughts. You can always express the numbers as the regular digits if that's more helpful towards getting that correct answer. All right, that's all. Thank you for listening.